So for the remaining topics in this course, we'll just be talking about series. Okay, so all about series that um, all about series that are included in our course. So for this session, we will define what a series is, and then we will also learn some techniques on studying the series. Okay, so let us start with this recall. So remember the infinite sequence, or we just call it a sequence. Okay, so a sequence which is denoted by this, okay, these curly braces, and then inside the curly braces it's just the an, or simply it's just your set containing a1 comma a2 comma a3 blah 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 blah. Okay, it's an ordered um, set of real numbers. Okay, and we said that this sequence is convergent if the limit of the terms as n approaches infinity equals L, where L is some real number. Okay? If L does not exist, or if L is plus or minus infinity, then we say that the sequence is divergent. Okay? So take note, a sequence, it's a listing of numbers. It's an ordered listing of numbers. Okay? Now, in several applications, we are interested in the sum of these sequences, or the sum of the terms in the sequence. So we are interested in finding what a1 plus a2 plus a3 until plus an plus 1 plus an plus 2 plus blah, blah, blah. Okay? We are interested in that sum. Okay? So this guy here, this sum here, okay? This sum here is what we call an infinite series, or simply a series. Okay? So a series, it's just the expression sum an, where n runs from 1 up to plus infinity. Okay? So it's just your a1 plus a2 plus a3 until plus an plus 1 plus blah, 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 blah. Okay? So remember your sigma notation when we were solving for the sum of finite number of numbers. Okay, you have a sub 1 plus a sub 2 plus until a sub n. It's just a finite number of numbers. Okay, that's also a series, but we don't usually call it a series. It's a finite series because it has only finitely many terms. Okay, so it's similar to this, except that you have infinitely many numbers to add. Okay, and as usual, these guys here, these a1, a2 until an plus 1, we call them the terms of the series. Okay, the terms of the series. So a natural question is, does this sum always exist? Can we always find the sum? Of course, if you have a finite number of numbers to add, you will always get the sum. If you just have 10 numbers to add, you will be able to get the sum by adding literally these numbers. If you have 100 numbers to add, you can find it. Even if you have 1 million numbers to add, it's still a finite number of numbers. You will be able to get the sum. Okay? Even if you have 1 billion, 1 trillion, 1 quadrillion numbers of number to add, okay? You will always get the sum. It will take a long time, of course, but you will get the sum. But if you have infinitely many numbers to add, can we always get a sum? So that's what we're going to study. And then we will learn several techniques, okay, to determine whether the sum exists or not. And if possible, we will try to learn how to get these sums, at least um, for some special series. Okay, so let us answer this question. Okay, for example, let us consider this series, the sum of n from 1 up to plus infinity. You have here 1 plus 2 plus 3 plus 4 plus 5 plus blah, blah, blah. And as you can see, as n increases, the sum just becomes very, very, very large. And if your n does not stop because it goes to plus infinity, okay, you are adding infinitely many numbers, okay, and you just have your natural numbers to add, then the sum becomes infinite, okay? So this guy here, the sum will not exist, okay? How about this? Let us take the series 1/2 plus 1/4 plus 1/8 plus 1 over 16 plus blah, 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 plus the general term can be written as 1 over 2 to the n. And then, of course, the next term, 1 over 2 to the n plus 1. So you see, this is just 1/2. 1/4, it's just 1/2 squared. 1 over 8, it's just 1/2 cubed. 1 over 16, that's your 1/2 to the 4th power, etc. So the general term, it's 1 over 2 to the n. Okay? So you want to add this. Okay? So in sigma notation, this guy here is just 1 over 2 to the n, and from 1 up to plus infinity. Okay? This is that sum. Okay? So can we get the sum for this if possible? Or does this guy here have a sum? Let us consider the first n terms. For example, in here, let us consider the first two terms. We just have 1/2 plus 1/4. That's 3/4 or 0.75. 0.75. Suppose we add the first three terms. You have 1/2 plus 1/4 plus 1 over 8. You'll get 0.875. Let's get the first four terms and then add them. You have 1/2 plus 1/4 plus 1 over 8 plus 1 over 16. You'll get 0.9375. Okay? We continue the process. First five terms. You'll get this number here. Okay? First six terms. Actually, this guy here, it's the first six terms. You'll get this number. Then you have the first seven terms. You'll get this number. Okay? So 1/2 plus 1/4 until plus 1 over 128. It's 0.9921875. And look at this, observe. From this up to this, okay, the difference between the two guys is just what? 0. About 25, 0.025. Oh, 0.125. And then from this guy to this guy, okay, so from this guy to this guy, if you get the difference, looks like this is just 0.125. 0.05. The difference, it's about 0.05. If you get the difference between these two guys, we'll get about 0.03. And then for these two guys, okay, this is about 0.01516, okay, 0.016. And if you look at this, okay, you'll have something like approximately, sorry, it's 16 here. So for here, you'll have something like 0.008. Okay. So from next term to the other, okay. So from, for example, from first two terms to the first three terms, okay, you have the difference between the two guys. Then first three terms to first four terms, the difference between the two guys, okay, it's smaller compared to the previous one. And as you proceed down the ladder here, the difference between the two guys becomes smaller. And you even go down further, the difference will be smaller and smaller. Okay? So in here, it seems that the series approaches one. Okay? So meaning if you have infinitely, maybe you have added the first 100 terms, you might get 0.9999 and then something that is not 9, etc. So I said 4 nines there. And then maybe if you increase the number of terms that you will add, say the first 1 million, then what you will see, the sum would be 0.99999, so many nines, before you will get something that is not equal to 9. Okay? Follow? In fact, if you add all of this, okay, if you add all of this, all the terms, what you will actually get is 1. Meaning the sum of 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc., you will actually get 1. Okay? And we say that the series has a sum. Okay? Now, you look at this process. You look at this process. We added the first two terms, and then the first three terms, and then the first four terms, first 5 terms, etc. We will generalize that. We will generalize the process. So when does a series have a sum? Okay? Let us denote S sub k. Okay? Let us denote by S sub k the sum of the first k terms in the series. Sum A sub n from 1 up to infinity. So this means your S sub 1, it's just your A1, the first term. S sub 2, it's the sum of the first two terms, A1 plus A2. S sub 3, it's your A1 plus A2 plus A3. And if you continue this, your S sub k, this will be A1 plus A2 plus A3 until plus A sub k. Okay? So you add the first k terms. And you can get the sum of this, actually the sk, because you just have a finite sum. Okay? Now, this S sub k, it's called the kth partial sum of the series. It is the kth partial sum of the series. partial. So you only add partially. Okay? Now, you have the S sub k. You form the sequence whose terms are the S sub k's. You have the S1, S2, S3, etc. Those will be the terms of this sequence here. We call it the sequence of partial sums. Okay? So, we have a sequence of partial sum. How does this one relate to our series? We have this SK. How is it related to our series? So notice, we can talk about the limit of the sequence as k approaches infinity. Okay? And this is just a sequence, so we can solve this. We've discussed this. We know how to do limits of sequences. But notice, what does this mean? You will have the limit as k approaches plus infinity of the sum a sub n from 1 up to k. Okay? And this guy here, if you let your k approach infinity, this could equal to the sum from n equals 1 up to plus infinity of a sub n. So now we are back to this guy. So if you notice, if this guy here has a limit, the quotation marks here will disappear. The limit, if it exists, will be the sum of this. Okay? So let a sub n from 1 up to plus infinity be a series. And we denote by S sub k the sequence of partial sums of this series. If the sequence S sub k converges to S, meaning if the limit of S sub k as k approaches infinity equals S, then this series here is said to be convergent. Okay? The series here is said to be convergent, and the sum, it is equal to S. It is equal to the limit of the sequence of partial sums. Okay? If this sequence of partial sums diverges, then the series itself is divergent, meaning you will not be able to get the sum. Okay? So this is the definition way of determining whether the series has a sum or not, with the use of the sequence of partial sums. Okay? So in other words, a series AN is convergent if its sequence of partial sums is convergent. And we now have the following. Okay? The series n from 1 up to plus infinity, it is equal to the limit as k approaches infinity of the series n from 1 up to k. But this guy here, it's your sequence, it's your partial sum S sub k. So you have the way, at least by definition, you have a way to find the sum of a series. Okay? For example, determine whether this series 1 over n times n plus 1 and from 1 up to plus infinity converges or diverges. Okay? So at this point, what we only know is the definition, meaning we just use sequence of partial sums. Now, first, let us rewrite this 1 over n times n plus 1. Remember your partial fractions when we discussed integration by partial fractions? We'll start with that. Okay? So it means you will have something like a over n plus b over n plus 1. And then you combine, you have a times n plus 1 plus b times n divided by n times n plus 1. So you will have a n plus 1 plus b n. This is equal to 1. Okay? And notice that if n equals 0, then you'll just have a equals 1. Okay? And then if n equals negative 1, if n equals negative 1, this guy here will be equal to 0. It's negative 1 plus 1, that's 0. So you'll just have here, then you will have negative b, it's equal to 1, or you have b equals negative 1. Okay? So what does this mean? Your 1 over n times n plus 1, this is simply 1 over n minus 1 over n plus 1. Okay? So the question was, is that allowed since the sum, it starts from n equals 1? Actually, when we do this, okay, when we do this, we don't, when we do this, we don't think of n as some number that starts only from 1. It's just another, you think of n here as some variable. Okay? So this is allowed. This is allowed. Because what we are just going to do is to decompose this guy here. That's a good question. Okay? All right. So we were able to decompose 1 over n times n plus 1 into 1 over n minus 1 over n plus 1. Which means that in here, the sum 1 over n times n plus 1, and from 1 up to plus infinity, we can rewrite this as the sum from 1 up to plus infinity of 1 over n minus 1 over n plus 1. Okay? Now, let us look at the partial sums. Let's have S sub 1. S sub 1, it's just your A1. So it's your first term. This is what? 1 over 1. I'll just write that 1 over 1 as 1. So you have 1 minus 1 over 1 plus 1. So you'll have here 1 half. Of course, you may calculate this. This is just 1 half. But I'll not calculate that one. Let's consider S sub 2. S sub 2, it's A1 plus A2. And this is equal to your A1, it's 1 minus 1 half, plus your A2. So when n equals 2, you will have 1 half minus 1 over 2 plus 1. So this is 1/3. And in here, observe, this is negative 1 half, this is positive 1 half. So this is simply 1 minus 1/3. Okay? 1 minus 1/3. Let me continue the computation on next page. So this is your A sub 2, S sub 2. So let us recall, this guy here, it's equal to the sum 1 over n minus 1 over n plus 1. N from 1 up to plus infinity. Now let's have S sub 3. Of course, S sub 3, it's A1 plus A2 plus A3. For A1, we have 1 minus 1 half. For A2, we have 1 half minus 1/3. For A3, we have n equals 3. So we have 1/3 minus 1 over 3 plus 1. So this is equal to 1/4. And observe, this minus 1 half will cancel the plus 1 half. This minus 1/3 will cancel the plus 1/3. So this guy here, it's just 1 minus 1 over 4. Let's have S sub 4. You have A1 plus A2 plus A3 plus A4. We already have this guy here. It's actually this guy. So let's just write that. That's 1 minus 1/4 plus A sub 4. A sub 4, you will now have 1 over 4 minus 1 over 4 plus 1, which is 1 over 5. And as you can see, this will disappear and this guy here. So you will have 1 minus 1 over 5. Okay? If you continue the process, your S sub k, it will be something like, well, you have by definition A1 plus A2 plus A3. You continue plus you have A k minus 1 plus A k. Okay? So if you enumerate all the terms, you'll have 1 minus 1 half plus 1 half minus 1/3 plus 1/3 minus 1/4 plus blah blah blah. At k minus 1, you will have 1 over k minus 1 minus 1 over k minus 1 plus 1. Correct? K minus 1 plus 1. And then your A sub k, this will be 1 over k minus 1 over k plus 1. And observe, this will cancel the next term here. This guy will cancel the next term here. This guy will cancel what is in here. This guy, it will cancel the one before that. So this guy here, it will cancel the one before that. And this guy here, it's k minus 1 plus 1. So it's just 1 over k. You have that 1 over k, that's minus there. And then you have 1 over k here, that's plus. So this guy will cancel this guy. And your S sub k will just be 1 minus 1 over k plus 1. Okay? So if we get the limit as k approaches plus infinity of S sub k, this is just the limit as k approaches plus infinity of 1 minus 1 over k plus 1. But as k goes to plus infinity, this will just go to 0. And we have a limit. It's equal to 1. So what does this mean? Therefore, the sum 1 over n times n plus 1, and from 1 up to plus infinity, this is equal to 1. Okay? Questions? Next, show that the harmonic series 1 over n is divergent. This guy here, the name is there. It's called harmonic series. Okay? It's called harmonic series. The harmonic series, so 1 over n, n from 1 up to plus infinity, this is 1 plus 1 half plus 1 third plus 1 fourth plus etc. So we want to show that this is divergent. Meaning, if we use the partial sums, the sequence of partial sums, we will get greater than, we will get plus infinity. Okay? When we take the limit of that sequence of partial sums. Now, here's what we're gonna do. I'll try to add some more terms. You have 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus etc. Okay? Now, start with S sub 1. This is just A1. This is just 1. Okay? Next. Instead of calculating S sub 2, I will calculate S sub 4. In fact, let us calculate S sub 2. Let's just calculate S sub 2. S sub 2, it's just A1 plus A2. This is 1 plus 1 half. 1 plus 1 half, this is greater than 1. Okay? Let us now look at S sub 4. Look at this. A1 plus A2 plus A3 plus A4. This is equal to 1 plus 1 half plus 1 third plus 1 fourth. Okay? Now, 1 third, it's greater than 1 fourth. Correct? 1 third, it's greater than 1 fourth. Correct? So, this is greater than 1 plus 1 half plus 1 fourth plus 1 fourth. But look at this. 1 half plus 1 fourth plus 1 fourth. That's equal to 1. Correct? So this guy here, it's equal to 2. Your S sub 4, that's greater than 2. So S sub 1, S sub 1 here, it's equal to 1. S sub 2, it's greater than 1. S sub 4, it's greater than 2. Okay? Now, let us look at S sub 8. S sub 8. Of course, this is A1 plus A2, etc. until plus A sub 8. So if we enumerate this, 1 plus 1 half plus 1 third plus 1 fourth plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. Okay? 1 over 5, if you look at this, 1 over 5, it's greater than 1 over 6. It's also greater than 1 over 7. It's also greater than 1 over 8. Okay? So, this guy here will be greater than, you have your 1 plus 1 half plus 1 fourth, 1 third plus 1 fourth, and then plus 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. Okay? So there was a question, why we have twice 1 fourth here? Well, 1 third, it's greater than 1 fourth. That's why we have the inequality here. This guy here, it's larger than this because 1 third, it's greater than 1 fourth. Okay? And then same concept for this. Your 1 over 5, 1 over 6, and 1 over 7, they are all greater than 1 over 8. So we have this inequality here Our 1 over 5, it's greater than 1 over 8. 1 over 6, it's greater than 1 over 8. 1 over 7, it's greater than 1 over 8. 1 over 8, it's equal to 1 over 8. So we don't change that. But what is this guy? This guy here, it's just 1/2. Okay? So this is just, if we calculate this is actually 2.5. So for this, let me change this instead. This is equal to 1.5. But what does this mean? S sub 8 here, okay? Your S sub 8 in here, it's greater than 2.5. Okay? You can check. You can check that if you calculate your S sub 16, this will be greater than 3. Okay? Your S sub 16 will be greater than 3. So what does this mean? What can we conclude from here? What can we conclude from here? We have S sub 1, well, it's just equal to 1. S sub 2, this is greater than 1, correct? S sub 2, it's greater than 1 because it's 1.5. S sub 4, S sub 4, you can write it as 2 to the 2, correct? S sub 4, it's 2 to the 2. It's greater than, you look at this, S sub 4, it's greater than 2. So let me just write it here. It's greater than 2. And of course, 2 is greater than 1. Now, S sub 16, this is S sub 2 to the 4. Okay? So, in here, we will have this guy here, it's greater than 3. Okay? And this is, well, this is greater than 2, 2 minus 1. Actually, let's just put that as greater than 3. Or, of course, 3, it's equal to 4 minus 1. There was a correction there. Nice spot. We replace this guy here. Okay? We replace this guy here by 1/4. Well, 1/3, it's greater than 1/4. So we replace this by 1/4 in order to get 2.5. That is correct. Thank you for that. So we have here 1/4. And still the inequality here, it's still correct. Okay? You will be able to show that S sub 16 um, it's greater than 3. Okay? Your S sub 32, this is S sub 2 to the 5. If you calculate this is 3 point, this is greater than 3.5. Can you see the pattern there? 1, 1.5, 2, 2.5, then 3 in here. This will be greater than 3.5. Okay? And then you have your S sub 64. This is S sub 2 to the 6. This is greater than 4. Okay? And this guy here, well, it's 5 minus 1, but I don't want to use this. But it's 5 minus 1 there. Okay? So can you see the pattern? So it seems that as we increase the subscript for S, okay, as we increase the subscript for S, the sum actually increases in a sense that it's always plus 1 or plus 0.5 depending on the pattern that we see in here. Correct? So, in fact, what we can conclude, or if we continue the process here, what we can get is the following. Your your partial sum, okay? Your partial sum in here, we will get, so we have the subscript. So you have your S, and then we have the subscript for S. So say your S sub 2 to the K, this is greater than and K plus 1 over 2. Okay? Correct? You see, if your K equals 0, if your K equals 0, that's 2 to the 0, that's 1. So 0 plus 1, it's 2, it's 1 over 1. 0 plus 1, it's 1 over 2, that's 1 half. And we see it here, greater than 1 half. If K equals 1, then that's 2 to the 1. So you are looking at S sub 2. Okay? But S sub 2, so 1 plus 1 over 2, that's just 1. So you got this guy here. Okay? And then you have K equals 2. So you are at this point. Okay? And we said that it's greater than 2. When K equals 2, you have 2 plus 1 divided by 2. That's 3 halves. So this is what we have. This is greater than 1.5. And then here, this is greater than 2. That's what we know. And then this guy here, this is greater than 3. Okay? So when k equals 4, so we are here. When k equals 4, 4 plus 1, and that is equal to, so we have here, this is greater than 2.5. That's why I am confused because I skipped S sub 8. S sub 8, that's S sub 2 to the 3. And this guy here, it's greater than 2. So you can insert that, etc. So for any k, S sub 2 to the k, it's greater than k plus 1 over 2. So what does this mean? The limit of S sub 2 to the k approaches plus infinity, okay? K approaches plus infinity. This is greater than the limit as k approaches plus infinity of k plus 1 over 2. But this means this is plus infinity here. So it means that this sum here, this limit here must be plus infinity. So the limit of S sub 2 to the k as k approaches plus infinity, this is plus infinity. But in the end, if you let your k approach infinity, you're just getting S sub infinity. This S sub k as S sub 2 to the k, if you get the limit of this as k approaches infinity, this will still be 1 over n from 1 up to plus infinity. You're just skipping the terms in the sequence. You have S sub 1, S sub 2, S sub 3, S sub 4, S sub 5, etc. But you just ignore your S sub 3, S sub 5, S sub 6, and S sub 7. You ignore that. Okay? Still, the sequence of partial sums, in here, let me write S sub k still. K from 1 up to plus infinity, this diverges. So is divergent, and therefore the harmonic series is divergent. Okay? Questions? So that's how we show that this harmonic series is divergent. Okay? Any questions? So harmonic series. So it's a name, the usual name for this series. So if I say, or if I ask you to use the harmonic series, it's this guy here. Sum of 1 over n from 1 up to plus infinity. Now, let us consider this series. It's just a series with a name. Okay? We call it the geometric series. So the geometric series, it is of the form, this guy here. Sum a r raised to n minus 1, n starting from 1 up to plus infinity. Okay? So this is a plus ar squared plus ar cubed plus ar to the fourth, etc. Where here, a it's a constant. R, it's also a constant. Okay, they are both non-zeros. Okay, this R here has a name. We call it the common ratio or simply the ratio. Okay, and A here, in this particular form, A here, it's your initial term. Okay, so we call this the geometric series. Sometimes you will see something like this. Sum A r to the n starts from 0 up to plus infinity. They are the same. Look, when n equals 1, because you start from 1, when n equals 1, you have r raised to 1 minus 1. That's r to the 0, correct? When n equals 2, you have 2 minus 1. That's r to the 1. If you look at this, you start with n equals 0. So when n equals 0, you have here r to the 0. That's the starting point also for this. When n equals 1, you have r to the 1. That's the second point in here, or the second term in here. So this guy here, it's the same as this guy. So you might see this or this one. Okay? Later, we will be having series where we start with n equals 0. Okay? So, for this geometric series, we would know whether this series is convergent or divergent depending on the value of r. Okay? Depending on the value of r. So here's the theorem. Suppose you have the geometric series a r raised to n minus 1 and starting from 1 up to plus infinity. Then this series is convergent if the absolute value of r is less than 1. Okay? And the sum, the actual sum, can be calculated using this formula. The sum ar raised to n minus 1 and starting from 1 up to plus infinity, it's equal to a over 1 minus r. Okay? On the other hand, this series is divergent if the absolute value of r is greater than or equal to 1. Okay? So the series is divergent if absolute value of r is greater than or equal to 1. Okay? Let me show how we can calculate this and hence proving this series. Okay? So let me get a blank space in here. So let me use this space. So we have the geometric series a r raised to n minus 1 and from 1 up to plus infinity. So this is just a plus ar plus ar squared plus etc. Okay. Now, let's consider S sub k. S sub k, it's It's a plus a r plus a r squared plus until we have a r to the k. Now, I'll take this s sub k and multiply r. So this guy here, we multiply each term by r. So we will have ar plus ar squared plus blah 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 plus ar to the k plus ar to the k plus 1. Following? Okay? And then what we're going to do is to subtract s sub k minus r s sub k. If we subtract that, notice this will cancel this. This will cancel this. This guy here will cancel this. What will remain is a minus a r raised to k plus 1. And then, well, we factor out s sub k on the left side. So s sub k times 1 minus r. On the right side, we factor out a. So you have here a times 1 minus r raised to k plus 1. Okay? Following? And therefore, s sub k here, this is simply a times 1 minus r to the k plus 1 divided by 1 minus r. Okay? So there was a question, how did we get this? Well, from s sub k, we just multiplied by r. We started with s sub k. And then from the s sub k, we just multiplied r. So we multiply this by r, you'll get your ar. You multiply this by r, you get ar squared. You multiply this by r, you will get ar cubed in here. You multiply this by r, you will get that ark plus 1. Okay? Now, look. If r it's greater than 1, okay? If r it's greater than 1, then recall from your Cal 1 the limit of r to the, say, to the k plus 1 as k approaches plus infinity. This will go to plus infinity. Okay? Why? This is just exponential. You can think of this, okay? You can think of this as your function y equals a to the x. No, I'm not gonna use x. I'm not gonna use a. Let me use b to the x. You have the graph of that to be something like this if b is greater than 1. Okay? Recall that from your Cal 1, the exponential functions. If b is between 0 and 1, then we will have, sorry, why b? If absolute value of r is between 0 and 1, then the limit of r to the k plus 1, okay? Let me put absolute value in here. Absolute value of r raised to k plus 1 as k approaches plus infinity, this will be equal to 0. Okay? And recalling from your Cal 1, okay? Again, you have your y equals b to the x. The graph of that is something like this. It approaches 0. So here, if 0 less than b less than 1. Okay? So what does this mean? The limit of sk, sk approaches plus infinity, this is equal to the limit as k approaches plus infinity of a times 1 minus r to the k plus 1 over 1 minus r. Okay? This is equal to, a over 1 minus r if absolute value of r is less than 1. Okay? Also in here, this is absolute value. Let me put the absolute value there. Of course, we put the absolute value in here. Okay? And then, of course, this guy here, it's plus infinity if the absolute value of r is greater than 1. In fact, we also have the equality in here. If absolute value of r equals 1. Actually, no. This guy here, it's not always plus infinity if that's the case. So I'll just remove this. Okay, I'll just remove the equality there. Okay, and then actually that's not plus infinity here. It's infinity times the sign of a. It's infinity times the sign of a. Because if a is negative, then you will have negative infinity. If a is positive, then you will have plus infinity. So let me write that. So instead of sign a here, I'll just write plus or minus infinity. Plus infinity or minus infinity. Now, we have that. We also have the case or r equals 1. And then the other guy does not exist. The limit does not exist if your r here this is equal to -1. Okay? Because it could be plus infinity, it could be minus infinity. We don't know actually. So because of this analysis, we have the theorem. Okay? We got this theorem. Convergent has a limit, okay? And the limit is this guy. If your R in absolute value is less than 1. And divergent could be plus infinity, could be minus infinity, could be does not exist. So divergent if the absolute value of R is greater than or equal to 1. Okay, there is a very good question in here. Why do we allow R equals 1 if the denominator is 1 minus R? This guy here, 1 minus R, actually will cancel the 1 minus R coming from here. Take note, you are only considering limit. Okay, you are only considering limit. If actually R is not equal to 1, the 1 minus R will cancel. This guy here will have a factor 1 minus R. It will cancel this one. Okay? That is if R is not equal to 1. But again, what if R is equal to 1? Let us try to write that. Okay? Let us try to elaborate that part. If R equals to 1, you just have here. Correct? Sum of A and from 1 up to plus infinity. Because any power of 1, it's just 1. So this is A plus A plus A plus A, etc. But you are correct there. You are correct there. I should have not included this guy here if I am looking at this. Okay, because we don't have that 1 minus R. But if only I am looking at this SK, then I have this part here. Meaning, at this computation here, we are assuming R to be not equal to 1. So that is a very good question. Let us actually write it here. Okay. So in here, if R not equal to 1. If R equals 1, then we can just have this part here with R equals 1, and that's this guy. Very good question. Okay? But still, coming from here, if R equals 1, then it could be plus A or plus infinity or minus infinity. I mean the limit. Okay? So the question is, should we remove the R? No, we don't have to remove that one. We don't have to remove this case here because the answer is still the same, plus or minus infinity. This is what we are trying to look at for this. Okay? Other questions? Okay. So hence we have this theorem. Let's have this. Determine if the series pi raised to n minus 1 over 3 to the n converges. If it does, find the sum. Okay, let us start with this series. Remember, our geometric series is of the form a r to the n minus 1 and from 1 up to plus infinity. And I said also that it could be of the form a r to the n and starts from 0 up to plus infinity. But in here, our given series, it's pi raised to n minus 1 over 3 to the n. And we have here n from 1 up to plus infinity. So if our n starts from 1, let's rewrite this series here into this form. Note, this guy here, you can write it as pi raised to n minus 1 over 3 times 3 to the n minus 1. 3 times 3 to the n minus 1, that's 3 to the n. Here you have n from 1 up to plus infinity. We separate this denominator 3, and then we put these guys here into a single exponent. So this guy, it's just n from 1 up to plus infinity of 1/3 times pi over 3 raised to n minus 1. So now, we have this form here. Okay? Now, pi over 3, this is greater than 1. Correct? Your pi over 3, it's approximately equal to 3.14. So it's greater than 3. So something greater than 3 divided by 3, it's greater than 1. So pi over 3, it's greater than 1. That's your r here. Okay? So, by the geometric series test, I'll just write it as geometric series test. Series test. It's a test that we use in order to identify or in order to determine whether the geometric series is convergent or divergent. By the geometric series test, the series pi raised to n minus 1 over 3 to the n, and from 1 up to plus infinity, this guy here is divergent. Okay? Questions? Next, consider the series negative 2 to the k over 3 to the k minus 1, and then k starts from 0 to plus infinity. Determine whether this is convergent or divergent. If it does, if it is convergent, find the actual sum. In here, we have k equals 0. We have k equals 0. And like I said, if you start with k equals 0 or n equals 0, then the power of your r will just be n and not n minus 1. So this is the one I'm saying. The power of n here, r here, it's just n because you start n equals 0. So therefore, for this, let us adjust our series. We have the series starting from 0 up to plus infinity. you have negative 2 to the k divided by 3 to the k minus 1. This guy here can be written as series from 0 up to plus infinity negative 2 to the k divided by 3 raised to negative 1, 3 raised to k. Or this guy here, this is just the series. K from 1 up to k from 0 up to plus infinity of 3 times negative 2 over 3 raised to power k. Okay? Since the absolute value of negative 3 over 2, this is just 2/3, and this is less than 1, correct? That's your R, negative 2 over 3. So we are calculating the absolute value, and we found it's less than 1. The series here, negative 2 to the power k over 3 to the power k minus 1, k from 0 to plus infinity. This one here is convergent. Okay? With sum, you have 3 over 1 minus negative 2 over 3. Okay? So this is equal to 3 over 1 plus 2 over 3. Let's just add this. You have 3 over 3 plus 2 over 3. So this is equal to 9 over 5. So that's the sum of this series here. Okay? So take note, we have to do this because we need to identify the tree. Okay? We need to identify the tree here. Actually, the A there. We need to identify the A there. And that's your numerator A in here. This guy here, it's your R. So you have here 1 minus R. So you have 1 minus negative 2/3, and that's just 1 plus 2/3 in the denominator. 1 plus 2/3, that's 5 over 3. And there's a numerator 3 here. So it's 9 over 5. Okay? Some properties of infinite series. If you have two convergent series here, series AN and series BN, with the same starting point, n equals 1, and they are both convergent, then this series here, okay, you either add or subtract term-wise. Okay? So the series AN and the series BN are convergent. Then the series A plus or minus BN is also convergent. Furthermore, the sum of this series, okay, the sum of this series is just the sum of the sum of the two series. Okay? So meaning, you can distribute this summation symbol or sigma notation. Very much similar to the finite sum when we discussed this in our first meeting. Just keep in mind, they must have the same starting point. Okay? Now, if C is not equal to 0, and you have a series AN which is convergent, then this guy here is also convergent. The series with terms C times AN. And the sum of CAN will just be equal to C times the sum AN. So meaning, this constant here, you can bring it outside of your summation symbol. If this series here is divergent, okay, the series AN is divergent and your C is not equal to 0, then so is the series CAN. Okay, this will also be divergent. Okay, and then here, for any positive integer k, here you have the series which starts from n equals 1. Here, you have a series which starts with n equals k. So you have these two series, the same terms, except that in here you start with n equals 1, in here you start with n equals k, meaning you drop the first k minus 1 terms for this guy here. Then both of them are convergent or both of them are divergent. They have the same convergence. Both of them are convergent or both of them are divergent. So whether you start with n equals 1 or n equals 10 or n equals 100, etc., they will have the same conclusion. Both of them convergent or both of them divergent. If they are both convergent, the actual sum will be different. Of course, because in here you started with n equals 1. You are adding all the terms. On the other hand, in here, you dropped the first k minus 1 terms. Correct? So the sum here will be less than this guy here if your AN are all positive, or if your AN, if you don't know whether they are positive or negative or combination, well, the sum here will be different from the sum in here. Okay? Questions? Now, we discussed series. We defined what a series is. We had a way of finding or determining whether the series is convergent or divergent. It's via the definition, via sequence of partial sums. If we study the sequence of partial sums, we will actually get an actual sum or not. And then we have the harmonic series. We know that it is divergent. And then we have the geometric series. The geometric series, we have a way of finding the actual sum if it is convergent. But more importantly, we can determine whether it is convergent or divergent by studying the common ratio or the ratio. Okay? We have another way of determining whether the series is convergent or divergent. In fact, this one here, we have a way to determine whether the series is divergent or maybe not divergent. We call this the divergence test. Here's the theorem. If we have a series AN which is convergent, then the limit of the terms here must go to 0. Okay? So you have a sum AN and you found the sum to be convergent. Then the terms, those terms that you were adding, okay, the terms must go to 0. Okay? Okay? So let us prove this. Proof. Let AN and from 1 up to plus infinity be a convergent series. Convergent series with sum S. Okay? Consider the sequence of partial sums. Consider S sub k. Okay? Then S sub k minus S sub k minus 1. This is equal to A sub k. Correct? So you have S sub k. You have A1 plus A2 plus until AK. You have S sub k minus 1. You have A1 plus A2 plus until A sub k minus 1 only. So if you subtract S sub k minus 1 from S sub k, this is just the remaining term. Okay? So, if we have the limit of k approaches plus infinity of A sub k, this is just the limit as k approaches plus infinity of S sub k minus S sub k minus 1. But this is just the limit as k approaches plus infinity of S sub k minus the limit of S sub k minus 1 as k approaches plus infinity. You can distribute the limit operator here because the limit exists. This is simply S minus S. And this is equal to 0. So that's our theorem. So again, you can only do this part here because the limit here and here, they both exist. So you can separate. Okay? Okay? So question, why is S minus S? Sk, it's the sequence of partial sum of your series here. Your series here, it's convergent. The sum is S. So what's the limit of Sk? It's equal to the sum, which is equal to S. That's the definition of our sum. So you have this. But this is the one we need. The corollary to this theorem. We call it the divergence test. It's actually the contrapositive of this guy here. So what does this corollary say? If the limit of your terms it's not equal to 0, okay? If the limit of your terms is not equal to 0, then your series is divergent. Okay? So if the limit of your terms is not going to 0, the series is divergent. Okay? So this theorem guarantees the divergence of the series if the terms do not go to 0. But warning, this is a very big warning. Listen very carefully. We have this theorem. If the limit of the terms is not going to 0, then the series is divergent. What happens if the limit is equal to 0? If the limit is equal to 0, we don't have any conclusion for the series. So if the limit of the terms is equal to 0, this series here may or may not converge. We don't know. Okay? So what's sure is, if the terms do not go to 0, automatically the series is divergent. If the terms go to 0, we don't know. Maybe convergent, maybe divergent. We will use another way or another method. To see this, you have your harmonic series that's divergent. Correct? That's divergent. But no, note that the limit of 1 over n here as n approaches 0, this is equal to 0. This here, we have shown that this is convergent. We calculated it. We actually have the sum. And notice the limit 1 over n times n plus 1 here, it's also equal to 0. So if we only study the terms and we found that the limit is equal to 0, we don't have any conclusion. It could be convergent, it could be divergent. I mean, the series could be convergent or could be divergent. Okay? So I'm bringing back this guy here. If the limit of the terms is not equal to 0, the series is divergent. So this is a divergence test. It is not a convergence test. Okay? It is a divergence test. Okay? It's a mortal sin to use this for convergence. Okay? Example, let's just look at this. Determine if the series, this guy here is convergent or divergent. Okay? So Let's do this separately. And then if both of them are convergent, then we will be able to find the sum. So first, let us analyze 1 over 2 to the n minus 1 and from 1 up to plus infinity. But this is just what? The sum and from 1 up to plus infinity of 1 half raised to n minus 1. Correct? Absolute value of r, this is just 1 half. Well, absolute value of 1 half, but it's 1 half. It's less than 1. So this guy here, this is convergent. And the sum, look at this. What is your A here? The A here, it's somewhere here. It's actually equal to 1. So basically, this is A equals 1, R equals 1 half. And therefore, you have 1 over 1 minus 1 half. This is equal to 2. Okay? Number 2, we have the series 2 over n times n plus 1. And from 1 up to plus infinity. But this is just what? We can bring out the 2 here. So we'll just have the sum of 1 over n, n plus 1, and from 1 up to plus infinity. But this is just 2 times 1, which is equal to 2. So the equality here, okay, using a previous calculation. Previous calculation. Okay? Meaning this guy here, we have calculated it to be equal to 1. Let me go back to that calculation. It's this part. Okay? And we ended up with this sequence of partial sum, and the sum, it's equal to 1. So that was the calculation. Okay? So we just use it here. Therefore, oops, let me use this one. Therefore, we have the series, and from 1 up to infinity of 1 raised 2 to the n minus 1, 1 over 2 to the n minus 1, plus 2 over n times n plus 1. This is just 2 plus 2, and this is equal to 4. Okay? Determine if the series e to the n over n squared converges or diverges. So for this, we only look at this. Let's hope that if we take the limit as n approaches infinity for this, we'll get something not equal to 0. Okay? So observe the limit as n approaches plus infinity of e to the n over n squared. Well, let us rewrite this as the limit as x approaches infinity of e to the x over x squared. This is infinity over infinity. So we can use L'Hopital's rule. We will have the limit As x approaches infinity, in the numerator, we still have e to the x. Denominator will have 2x. But this guy, it's still infinity over infinity. So we again apply L'Hopital's rule. We'll now have the limit as x approaches infinity. In the numerator, we still have e to the x. Denominator will just have 2. And look, this is equal to plus infinity. Okay? So, limit of e to the n over n squared as n approaches plus infinity, this is not equal to 0. By divergence test, the series e to the n over n squared and from 1 up to plus infinity is divergent.